Okay, hello and welcome to my channel. Today, we're gonna again take a look at what we have got from the last video and gonna investigate further into this function right here. Right, so first things first, I want to convert this back to x. So what to do here is you take x to equal to cosine theta. Right, so now you can get your ddx is equal to minus 1 over sine theta dd theta. Right, so we want this chunk right here. So from what we got, you can figure out that sine theta dd theta is equal to minus 1 minus x squared ddx. Right, now we substitute this into these two terms, and both have a minus sign, therefore you can just write the plus sign. So I will just write 1 minus x squared ddx. 1 minus x squared ddx PLM plus plus 1 sine square minus m square PLM equals 0. Okay, so can we do anything further to shorten this? Because it's still pretty long and messy. Well, you can shorten the sine square here as well, since cosine square theta is also equal to 1 minus x squared, which is cosine square. Okay, so this, you can further shorten this to ddx 1 minus x squared ddx plus this guy is now just LL plus 1. This guy now have a sine square, and I will write this as 1 minus x squared PLM equal to 0. Okay, so now you have successfully isolated this L term, which is our important term, since the M, well, essentially it does do something, but it is not as important and as prevalent as the L term in the polynomial. Okay, so from there, what you can do now is you take your M to equal to 0. So now our function can be rewritten again to ddx 1 minus x squared ddx on PLM plus L plus 1 PLM equals 0. Okay, so from here we can already begin to sort of one step forward to our recursion relation. So let's try taking PLM and expand it as a series k ak xk, because this is a function of x. Okay, so expand it. What you get from here, you squeeze this term, is the two-step. So find somewhere to write it here. The first one is when you squish it with these two derivatives to the 1. So that is a two-step k plus 2 k plus 1. And one thing I will do is that I won't write the xk part, since it will cancel out eventually, and we only have to take our ak term. Right, so next squish is you squeeze the minus x squared. That will give you a k outside, so that is minus k plus 1 on ak, because, well, the second The square cancels out the steps. Okay, now our last term is just gonna be LL plus 1 LK. AK, I mean. Plus 1 AK. So from here you can see that this term is groupable. So group it as LL plus 1 minus KK plus 1 AK equals 0. Okay, so now do as we did in quantum harmonic oscillator. We isolate the A term. Right, so we want it to be in this. To now we'll expand this guy right here. K plus 2, K plus 1. Right. And so from here, we're gonna force it to truncate. I'll have to truncate. Okay, so with this thing, you want it to truncate. You can see it like almost immediately. You need L to equal to K. So go up, L has to equal to K. So you substitute it back to your polynomial with n now equals to 0. What you get is PL of x is gonna equal to 1 over 2 L factorial ddx L and x squared minus 1L. Okay, so this would be your polynomial with m equal to 0. And from here, what the people or one person did is that he put it in the general form, which is PLM of x. PLM of x, it is equal to 1 minus x squared m over 2 ddx m ddx m and PL x. Okay, so this is your generalized polynomial here, and this would solve the equation that we started with, which is a lot of sine, a lot of theta thing. That function is going to solve that, and the solution it gives, it would be bounded by minus L and L. So this is going to solve that equation, and the solution would be something from minus L to L. So, and this would have 2L plus 1 values. Alright, so that is called the Legendre polynomial, which is very cool in my opinion. And from this polynomial, you can, well, expand it and get a lot more things. For example, like the spherical harmonics, which we're gonna be looking at in the next video. And now that we have found the polynomial, that would also be the end for today's video. And goodbye.